Thanks for the invitation. It's really a great pleasure to be here. So today we'll be talking about joint work with Simon Barazer and Alessandro Giacchetto. First of all, I would say that I sort of feel sorry for my collaborators because I think today we'll spend most of the time not talking about our work, but also the work of the others. But I think it will be more interesting for you this way. I will start with hyperbolic geometry and some basics. A hyperbolic surface is just a surface which locally looks like the hyperbolic plane. Instead of giving you more precise definitions, I think everybody will just be happy with pretty pictures. So it's just a surface that locally looks like this, and slightly more globally will be something like this. And they don't only exist in mathematics, but also in nature. And yes. And we even eat hyperbolic surfaces. And they can also be very tasty. OK, cool. So now we are all experts in hyperbolic geometry. So the story that we'll be telling you started in 2010. So at the end of that year, 2 papers appeared on Archive. The first one, Pan's decomposition of random surfaces by Larry Goose, Hugo Pallier, and Robert Young. The second one, the growth of Wyatt-Peterson volumes and random hyperbolic surfaces of large genus by Mariam Mirzakhani. The 2 papers look quite different, but I think they essentially ask exactly the same question: what does a random hyperbolic surface of large genus look like? I think for the audience here, the keywords is really large genus. OK, so they did lots of things in these 2 papers, but let me just show you 2 results in Mirzakhani's paper that I think sort of represent the style of results that they were after. I will start with a very informal statement. I will give more precise definitions later. How to say? Roughly, if you pick a random Wyatt-Peterson hyper that I didn't define yet, a Wyatt-Peterson hyperbolic surface is of G. When the genus becomes very big, the thing happens with nearly a very high probability. First of all, the diameter of the random surfaces, the random surface will be bounded by 40 log G, which is quite surprising to me when I read this paper the first time as a geometer, because, for example, if you ask me to draw a surface of very large genus on a blackboard, I think the first idea that will come to my mind will be do something like this. Right? But it's clearly not typical in this sense, because if you just put genus on a line, the diameter will grow more or less like linear in G, which is much bigger than log G. But it turns out I'm not the only naive person in the world, because here is a very pretty picture that I found in this in an article in the Quantum magazine, reporting the work of Will Head and Michael Magee on a very similar topic. Is also a random hyperbolic surface with large genus, but with a different model. But anyway, I think they put this picture in the very beginning of the article. I think is supposed to represent what like a random hyperbolic surface of a large genus. But if you just put genus in this way, the diameter will just be more or less square root of G, which is already much smaller than G, but still very much bigger than log G. So the idea here is, for me, actually random hyperbolic surface of large genus is very hard to visualize, because it just twists in space in all direction, and it spreads in space very, very efficiently, and it's a bit crazy. OK, so on the other hand, Mirzakhani also managed to prove something about the spectrum of a random surface, and in particular the spectral gap. The spectral gap λ1 is just the smallest eigenvalue positive of the Laplace operator. I would say this almost is one of the most important numerical value that you can associate to a hyperbolic structure. It controls. It's closely related to the geometry and the dynamics of this surface, and it's essentially something about the diffusion as it controls, for example, the counting of closed geodesics, the trigger constant, which measures how the surface is connected, and also it controls the rate of the Brownian motions, for example. So Miyazaki proved that there exists a spectral gap, which is at least 0.002. And this result was improved about 10 years later, in 2021, by two groups of researchers. The first one, Wu Yunhui and Xu Yuhao in Beijing, and the second, Michael Lipnowski and Alex Wright in North America. So they managed to improve this number 0.02 very significantly to 3 by 16 minus an epsilon, but this epsilon is actually can be arbitrarily small. So it's really the first number which counts. And 2 years later, this was pushed again by Nalignan and Daraman and Laura Monk. This time they managed to replace, they proved that this number actually can be replaced by 2 by 9. And now many of you may have the question, and I can confirm that it's actually not evident that 2 by 9 is bigger than 3/16, but it's a computation, so it's actually true. But all this doesn't matter now anyway, because just last year, they managed to push this again to a quarter. And this time it's really optimal, meaning that even for deterministic surfaces, this is the best number you can get. Yes. And I still remember, I think I've given a similar talk in Paris last year, somewhere in Paris, and of course I was talking about the length spectrum, and for the background knowledge. For the background, I talk about this story, and it was a geometry and dynamical system audience, and everybody got super excited about the spectral gap story. And finally, all questions were about the spectral gap, and I think nobody really cared about what I talked after. But so here I want to say that actually all these people, so the first step of their proof, they use the so-called Selberg trace formula. They use the trace formula to transform this spectral problem to a geometric problem, and then they studied the geodesics on the surface. So even if you are only interested in the Laplacian spectrum, this talk could still be interesting for you. Okay, cool. Sorry, I just forgot to mention a very important point. You may think this is already the end of the story, but actually the topic is still very active. Just a few months ago, this result has been improved again. And of course, you can do nothing about this a quarter, but this is but Will Head, David Machera, and Drew Thomas in the audience managed to improve this epsilon by replacing this by a narrow term, which is a polynomial, and 1 over g. So in this very impressive paper, they use a completely different method that I think you will see in Joe's talk. Okay, cool. But so now, but you may still want to know, so what is a random hyperbolic surface for me? So what is a Weil-Petersen random hyperbolic surface? So when we talk about the random structures, we need a model, which is basically a sample space with a probability measure on it. And so for us, the model today that we'll be looking at will be we'll fix the topology of the surface and study all possible geometry. So the sample space will be the so-called moduli space of hyperbolic structures or of Riemann surfaces of fixed genus. And I will just call this simply the moduli space. Okay, so now we still need a probability measure on the moduli space MG, but just before that, let's take a closer look at this moduli space MG. So first of all, the good news is it's a very nice space. It's almost a manifold of finite dimension. Dimension is 60 - 6. And I say almost because it's actually an orbifold. So meaning that it has some topological singularities, but this is really the most friendly singularity you can imagine. So it's not really a problem, actually. The real problem is actually that its topology is rather complicated. Just to give you an idea of the scale of the problem, we can check its Euler characteristic. So the idea is if the absolute value of the Euler characteristic is very big, then the topology cannot be very simple. So here is some very simple examples of Euler characteristic. If you take the cube and its Euler characteristic as a sphere as a surface is actually the same as that of a sphere, which is equal to 2. It's like it stays invariant under this kind of deformation. But if you take the torus, it has Euler characteristic 0. I think this you all know. And in dimension 2, it's if you have a triangulation or a cellular decomposition of your surface, is basically a combinatorial question. You just do the counting of vertices, edges, and faces, and then you do an alternating sum. And Euler's formula tells you that it's always equal to 2 minus 2g. So when g is very big, this number gets very negative. Absolute value is very big, so the topology is complicated, I would say. So all these things can be generalized to a more general, like higher dimension, and even for orbifolds. So this question makes sense. So what is the Euler characteristic of the moduli space? So the smallest moduli space for closed surfaces is M2, of surfaces of genus 2. And it turns out that its Euler characteristic is -1 over 240, which is numerically, I would say, pretty small. And even better, if you double the genus, it gets smaller. So now we get a hope that maybe when the genus becomes very big, this number just converges to 0, and the topology might be very simple, right? But if you just keep going, this number just explodes very, very fast, and it's get out of hand very, very quickly. It's a bit embarrassing to see this, but actually one of the main reasons we are interested in this large genus business is for fixed but general genus, like genus G is equal to 20, there are very few things that we can see. But when you take this large genus limit, it just normally simplifies the whole situation. But unfortunately, I don't think it's the case for the topology of the modular space, which just gets more and more crazy. So one of the strategies to get out is instead of working directly with modular space, you work with its universal cover, which is a so-called Pashmian space. And because the topology is super simple, it's basically the same as the Euclidean space of the same dimension. And it's even better because this homeomorphism is given by the so-called Fenchel-Nielsen coordinates system. And another way to put it is the modular space is the quotient space of the Pashmian space, where the fundamental group of the modular space acts. And then you take the quotient, you get the modular space, and the fundamental group has also another name called mapping class group, if you may rings a bell. For some of you.
So I have a quick question. How do you actually see the Euler characteristic in terms of the mapping class group? So is there a way to compute the Euler characteristic in terms of the mapping class group?
Yeah. So basically, yeah, indeed. So the result that you just say is a paper, they basically of Donzaguirre and Hara, I think, Hara. They computed this Euler characteristic of the mapping class group. And the mapping class group, you need a negation of the mapping class group on the net space. And then, but finally, I think it's just equivalent to compute the Euler characteristic of the modular space. But I don't know if this answers great. Okay, cool. But so in case you have never heard about any of this, universal cover, whatever, is very good analogy to keep in mind, which will be enough for this talk. The modular space is sort of like the torus. And Pashmian space is sort of like the universal cover of the torus, which is R2. And the fundamental group of the torus is just Z2, and which acts by translation on R2. If you take the quotient, you get the torus, right? And I think a better analogy, if you know what is a map, The modular space is sort of like the set of all maps with fixed topology, which is a finite set. And the detachment space is maps, but is a set of maps, but with an embedding. And this makes it immediately infinite, but somehow easier from some other perspective. Okay, so just before talking about the differential Nielsen coordinate system, let me be more honest with you, because if you just Google the definition of attachment space, normally you won't find it defined as the universal cover of the modular space, but as the space of marked hyperbolic surfaces of genus G. So what does this mean? It means that you want to fix a topological surface sigma G, which has no geometry on it, no hyperbolic metric, purely topological. And then instead of considering the space of all surfaces, you consider the space of all surfaces equipped with a marking phi, which is a homeomorphism, from the reference surface sigma G to the surface hyperbolic surface X. But of course, you want to quotient not by some local deformation. Actually, I wrote this definition here just to show you the existence of a precise definition, but you are not supposed to read this now, because normally it takes a few minutes to get used to this. But I say the idea behind is it's basically the same as what people working graph theory do. So normally, when people do graphs, it's somehow easier. Instead of considering directly graphs, you consider a graph with a market point. Right? This point has become special on the graph. It has a name, for example, Pierre. But you know, the geometers, they're kind of OCD. So they always want like absolute control of the object they're looking at. So instead of just marking one point, they mark all points. So by the way, actually, there are names of the people in a workshop where I gave a similar talk very recently. I want to do the same for the people here, but I didn't find the participant list. So here it is. So what do you want to say? So the idea here is, but if you want to mark every point on the surface, you need another surface to do that. And this is why you need a topological surface, sigma G, to mark this hyperbolic surface. So by doing this, so basically what you are doing is take a cover of the set of all graphs or surfaces, and you want to take a maximal cover, and this is the so-called universal cover. And by doing this, you completely unfold this modular space. So the attachment space is very big, but its topology is almost trivial. Okay, so this is the idea. So now I can talk about what is the coordinate system on the attachment space, but to do this, we need to know what is the pair pans. So what is the pair pans? This is the pair pans. It's actually a topological object. It's just a sphere of 3 holes. Normally people draw it like this, but if you are a hyperbolic geometer, you will do something like this. So once you have pairs of pans, you can have pans decomposition. The idea is you can is a way of chopping your surface into pairs of pans. Formally, it's just a set or a sequence of curves on a surface gamma 1, 2, 3, satisfying the following conditions. First, you want every gamma to be simple, meaning that it has no self-intersection, it never crosses itself, and you don't want any intersection also between the gamma s. So basically, you want to avoid all possible intersection, and also you want this set to be kind of maximal, in the sense that if you cut your surface along all these curves, this will completely disconnect your surface. You get many connected components, and you want each of them to be a pair of pans. So for example, here is a pans decomposition because you have 2 connected components, and each one is homomorphic to a pair of pans, a sphere of 3 holes. Right, and it's order characteristic computation. If you manage to do this, you always have 3G minus 3 curves, and you have 2G minus 2 pairs of pans. So this 3 minus So up to now, everything is still topological. But if you have a hyperbolic metric on your surface, then you can like tighten all these curves to be geodesic. And then you can measure the length of all these geodesics. This gives you 3G minus 3 length, positive real numbers. So why we are interested in these period pans, basically because of the following fact. Given 3 numbers, positive numbers, there actually exists a unique hyperbolic period pans with geodesic boundary of length exactly A, B, and C. So they can serve as building blocks for hyperbolic surfaces. You can, for example, if you start with a hyperbolic surface with a Pan's decomposition on it, then you can get 3G minus 3 numbers, but you can almost back engineer this process. Meaning that if you only have 3G minus 3 numbers with a Pan's decomposition, which tells you which Pan's is glued to which Pan's, and since each block is rigid, you have only one possible piece, then you just follow the instruction given by this pair of the Pan's decomposition, you can just reconstruct your hyperbolic surface. So, but there is still another thing is when you glue together 2 boundary components of 2 period pans or the same period, but two boundary components, you can just glue this directly, or you can twist a little bit one of them and then glue them together. So this gives you another hyperbolic structure, and so there is another parameter to fix, and this is called the twist parameter. So basically, finally, for every curve, you have 2 parameters, the length and the twist parameter. But it turns out that is all you need to determine a point in the attachment space. And this is so-called Fenchel-Nielsen coordinate system. Okay, just to sum up. So once you have a Pan's decomposition of your surface, you get a homomorphism from the Euclidean space to your attachment space. And this is the Fenchel-Nielsen coordinate system. And our goal, it has been a will, but is we want a probability measure on the moduli space. But it's a bit too hard because it's complicated, but we can start with a measure on the attachment space. It's still too hard because I don't know what's happening here, but I know what has measures on the Euclidean space. For example, there is a God-given measure, which is the Lebesgue measure here. Then I can just push forward this Lebesgue measure here along this phi p. Okay, but the problem is actually this Pan's decomposition is not unique. For example, I can replace this middle curve by another curve, and it turns out to be another Pan's decomposition. And actually, there is an infinitely many Pan's decomposition. So this will give you infinitely many arrows here. And so you will, on the attachment space, you will receive infinitely many copies of Lebesgue measures, and there, a priori, there is no reason that they coincide. So the definition doesn't really make sense. The miracle is a corollary of something called the Wolpert magic formula. Actually, they do coincide. So all of these copies, actually, they are exactly the same Lebesgue measure on the attachment space. And people normally call this to be fancier, the Y-Peterson measure, but it's actually just the Lebesgue measure. And also is actually a corollary of the first statement. This Lebesgue measure on the attachment space is invariant under the action of the fundamental group, of the moduli space. Since the moduli space is a quotient of the attachment space by this action, and the measure is invariant, so it descends to the moduli space. The situation here is exactly the same for the Lebesgue measure on the torus. You have a Lebesgue measure on R2, which is invariant by translation, so it descends to the torus, right? So we have a measure here, but the situation is slightly more tricky. Is slightly trickier than the situation of a torus because torus is compact. But the moduli space is not compact, so a priori, the total mass of this measure can be infinite, which is a problem for us because we want a probability measure to normalize. Yeah. But also, it turns out that it's finite. So, the stars are aligned. So now we get a well-defined probability measure called the Y-Peterson measure on the moduli space of hyperbolic surfaces, and this is our model. We can now pick a random hyperbolic surface. And using this language, I can restate the theorem of Minkun about the diameter. You take the indicator function on the moduli space. So it takes values at x. So x is a point on the moduli space which represents a hyperbolic structure. So it takes value 1 if this hyperbolic surface has diameter smaller than 40 log g. Otherwise, it's 0. Right? It's an indicator function on the moduli space. Then you integrate this function against the Y-Peterson measure we just defined. And then we normalize this by the total volume. And Mingkun proved that this number actually converges as g goes infinity to 1. So the interpretation is just is something. So, but I mean, every time we just write this, it's a bit heavy. So I just will formally write. I will let xg be a random surface, and I see the probability that its diameter is bounded by 40 log g goes to 1 when g goes to infinity. I think everybody is happy with this notation. All right. Okay. So this is basically the first episode that I want to of the story that I want to tell you, and actually it took us quite a while to produce the second episode. I was so surprised when I was reading the paper because I thought Mingkun just discovered a whole domain and prepared the tool set and did some examples, but didn't bother to optimize everything. And there are still many things to do. But actually, during 7 years, nobody did any. I think almost nobody did anything. But still at the end of the year of 2017, there is another paper by, I think it was after the death of Mingkun. This paper appeared on Archive by Mingkun and Brian Battery. But really in this paper we see I would say the strength of the toolbox prepared by Mingkun and the precision of results you can get with these tools. I will start with a very concrete version of their results. You fix two real numbers, A and B, and you want to count geodesics. So for a given hyperbolic surface X, I want to know how many geodesics of length between A and B there are. And also there are closed geodesics and also primitive. Primitive just means that actually one geodesic can run on its image several times. They will be regarded as different geodesics, and primitive means that it just it just does this once, right? Okay, so what they did in their theorem is so for every x, if it's deterministic, this is just a number. But if you just plug in a random surface, it becomes a random variable. And you can ask, so what is, for example, the average? What is the mean value of this random variable? They proved that when g goes to infinity, this converges to this funny integral. I mean, this integral of this funny function on this interval that you started with, cauchy x minus 1 divided by x. And actually, what they really proved is this random variable converges in distribution to the Poisson distribution of the same parameter. And I don't think the audience here needs this, but still, let me do this. A variable follows a Poisson distribution of parameter lambda if the probability of y is equal to k is given by this formula. Yes. And also, this function will appear several times during the talk, so I will just give it a name and call this lambda x. But actually, what they proved is even stronger. It's really a theorem about the length spectrum. The length spectrum of a hyperbolic surface is just a subset of positive real numbers, which are length of primitive closed geodesic on the surface. So actually, to be more precise, it's a multi-site because you can have two different geodesics with exactly the same length. So I also want to take into account this multiplicity. So it's a multi-site. So what they prove is, if you consider the length spectrum of a random surface, you get a random multi-site, but you can which can be regarded as a point process on R positive. And they prove that this point process converges in distribution to a Poisson point process with the intensity function lambda, which is the function that we just seen before. Which is sort of surprising also to me, because this means that if you take disjoint intervals, you will get like asymptotically independent random variables. So for example, if you fix one interval like from 0 to 1, and the theorem tells you that you should expect when genus is very big, maybe, I don't know, like 2 geodesics. But if you pick a random surface, you get, maybe you see 100 geodesics, and then you see this is a very rare event, so maybe I can use this information to get a better prediction, because I know the geometry of the surface because it's very special. So I have a better prediction of how many geodesics there are of length from like 2 to 3, but the theorem tells you that is actually not the case. Yeah, but anyway, so and I was, I still remember I learned this theorem during my master internship, and I was completely shocked because for me, when the first step, when you prove something, you have to want to prove this thing. And I don't think I would have enough imagination or courage to want to prove or like to want to prove something like this. But after many years of experience, I think one of the first things that I learned during my thesis is when you want to study something for hyperbolic surfaces, especially for random hyperbolic surfaces of large genus, it's always a good idea to check what happens for graphs. So there is a parallel story for graphs. For a graph, you can, so k is an integer, positive integer, you can count the cycles. Count the cycles of length k. So of course, cycles are just closed loops with, you just pass by every vertex just at most once. And length of it is just number of edges forming this. And here I colored the cycles of length 3 in orange and length 4 in red. And then I can restrict the attention to the 3 regular graph with V vertices. And this is a finite set. Then I can take a random graph, and a uniform random graph of this property, and it's a classic result in the 80s by Bolobash and Wormald, saying that for any possible length, and if you do the counting, this random variable converge the distribution to the Poisson variable of this parameter. And so here you see this is almost exactly the phenomenon. You get a Poisson variable, and even for this mean, the average value the structure is very similar to here. It's something exponential divided by something linear. Here is exponential. Here is also exponential divided by linear. And you can also recover this too, because here is cosh, so it's exponential x divided by 2. So here you also get a 2 here. But on the other hand, you also see that you cannot really push this analogy like too far, because for example, length of a cycle can never be like a half or like pi. It can only be an integer number because it has some combinatorial nature. But this geodesic can be whatever, so it's completely continuous. So, and actually, it turns out this Poisson phenomenon is very universal. If you just if your model is not so degenerate, you always get a Poisson phenomenon. But this intensity function is very sensitive to the geometry of your model. And normally, you don't expect to get exactly the same intensity function here if you deform a little bit even your model. Okay, but now you have a question like, okay, I'm happy with the Poisson thing, but why should I expect exactly this function, the lambda function? The short answer for this question is I have no idea, but I can at least say something about why this function makes sense, at least asymptotically, when L becomes very big. So we can count the number of geodesics of length at most L, and it takes the expectation, and by the theorem, it converges when G becomes very big to this integral. And if you work a little bit, it turns out to be asymptotic equivalent to exponential L divided by 2L. And there is a super classic theorem in geometry and also dynamical system, first proved by, I think, Huber in the 60s, and then many different generalized versions has been worked out by many people, Selberg, Margulis, Sarnark, etc. And so, but by the way, here I want to thank the courtesy of Peter Boozer, who sent me this picture of Hoover that I just cannot find on the internet. So one of the simplest version of this theorem is you just take one hyperbolic surface, but whatever hyperbolic surface, whatever the genus is, whatever the geometry is, if you do the counting, you always get exactly the same asymptotic. The number of geodesics of length up to L is always asymptotic to exponential L divided by 2L, which coincides with this function here. So at least this function sort of makes sense when L becomes very big. Okay. And also, their theorem has a very cute corollary that I like a lot. Is they also managed to say something about the systole. The systole is the length of the shortest closed geodesic on the surface. So, for example, if your surface is this, and then the systole will just be the length of this curve. And they also figure out the expectation of the systole of a random surface when G-gon becomes very big converges to this number. So actually, they have a very explicit formula, but if you just fit this formula to Sage or Mathematica, you get this number. Okay. So if there is no further question, so now I will go to the talk about something quite different. By the way, how many times do I? How much? 9. Okay, cool. I think it will be. So this will be the second season of the story. Which will be something completely different, which is this map. But I think people here know perfectly what is a map, but still, let me give a very brief definition of a map. A map is just a graph, but this graph is drawn on a surface. In a way, it's also kind of maximal, because if you cut off the graph, you will get a disjoint union of polygons, or topological disks. So it has no topology in the complement. And we call each of these polygons a face of your map. Here are 2 examples of maps, which are actually exactly the same graph because it has just one vertex with 2 loops. But they're different maps because they're drawn on different surfaces. The first one on the sphere, the second one on the torus. So the first one has a genus 0, the second one has genus 1. And the first one has 3 faces here, 1, 2, and other face. And here it has only one face because it's square torus, right? So n will just be from now on the number of faces, and our map will literally be metric, meaning that the length of each edge is not necessarily 1, but it can be any positive real number, like 1/2 or pi. There is a very simple and fundamental family of maps called unicellular maps, which are maps with only one face. You can see this as like a surface or a map obtained by gluing a very big polygon. And the simplest example is the planar case, and in this case, you just get all these plane trees, which are, I think, fundamental objects in combinatorics. And the study of the maps, I think people here know much better than I do. Started basically in the 60s by Tutt, and since then people have proved so many impressive results, and one of which is, I would say, this theorem by Jean-François Le Gall and Grégory Mirmont in 2011 about this Brownian sphere, which is the scaling limit of uniform random plane triangulation or quadrangulation. I think, once again, I'm not an expert of this. I think people here know much better than I do, so I don't think I will tell you, I will spend much time on this. But the point is, for various reasons, people working traditionally in this domain, they pretty much focus on the case of genus 0. But for us geometers, it's also very interesting to study what happens when the genus is very big. And so, but fortunately, since very recently, finally, people in the community started to be interested also in this regime, large genus regime. And here is a paper appeared still at the end of year of 2021. So we work very hard at the end of the year. So this paper is by Zwante Janssen and Baptiste Louf. they study unicellular maps. Unicellular maps of fixed genus and fixed number of vertices. And once again, unicellular means you have only one phase. And they do exactly the same thing. They count number of cycles. But this time, you do a rescaling of the whole thing. You rescale the whole metric of your unicellular map by the global factor, which turns out to be 12g divided by v, then square root. So what they prove is the following: if the number of vertices and genus go to infinity at the same time, but g is very small compared to number of vertices, and then you just pick a uniform random unicellular map with genus G with V vertices, and then you recover exactly the same phenomenon. So it's a Poisson. The counting follows a Poisson distribution with this parameter. And once again, this Poisson phenomenon is not very surprising, but for me, it's quite surprising to have exactly the same intensity function appearing here. So that sort of suggests that the geometry of a uniform hyperbolic surface is very close to the geometry of a unicellular map, uniform, for some reason that I personally don't understand at all. And so I think the best thing we can expect, maybe there might exist some kind of dictionary. So once we have this dictionary, if you manage to prove something about the graphs, then you can translate this to a result about hyperbolic surfaces, which are normally much harder. But I think I'm still very, very far from this dictionary, and I don't even know what kind of conjectures to propose, which is at the same time reasonable and interesting. Okay, so finally, just one word about their proof. So their proof is quite different from the proof of Miyazaki and Petri. They heavily relies on this magic bijection due to Chapuis, Ferret, Fusy, which basically says that the unicellular maps are in bijection with plane trees decorated with some permutations. And so very, very roughly speaking, what they did is they used this bijection to transform this problem about unicellular maps to a problem about random trees and random permutations that we understand much better, and they solved the problem here. But the only issue or it's not a problem, but the feature here is this bijection breaks when the number of faces are not 1 or 2. So finally, I will just say a few words about our work. Unfortunately, we didn't manage to say anything about the origin of this phenomenon, that why you should expect this coincidence, but we sort of proved that this phenomenon is even more universal. It's not unique to this unicellular case. It also works for the case of when you have many faces. You fix a length vector of n positive numbers, and you consider the following set of metric maps, the genus G with n faces. And you also fix the length of each face. The length of a face is the sum of lengths of edges forming this face. And you also ask that your graph is not very degenerate in the sense that you don't want leaves or this fake vertex in the middle of an edge. And if you do this, since I'm running out of time, so please believe me that there is a natural uniform probability measure on this space. It's basically the Lebesgue measure, and people also call this Kontsevich measure to be fancy. But it's just the Lebesgue measure. Then you can take a uniform random map, and we prove that if you fix the number of faces, you let G go to infinity, you also want the sum of all these lengths of faces to be linear in G. Another way to put it is so the length of every edge is more or less 1. And in this case, you recover the same result. And just one word, okay, so here this theoretical prediction has been confirmed by experimentally, so by some numerical simulation. Just let me say one more word before, and then we'll shut up. About the proof, there is not for no reason that we use this notation, which MGN, which looks very similar to the moduli space of hyperbolic surfaces. Actually, consider a slightly more general hyperbolic moduli space of hyperbolic surfaces with geodesic boundaries of fixed length. And it turns out that these two sets are homeomorphic to each other. This is some classic result by Bodic, Eberstein, Low, and Panner. And actually, it's even better because this is work of this group of people who work, I think, mainly on topological recursion, the friends of Ali, but they also have this paper proving these two worlds are actually perfectly parallel, meaning that all the tools you have here, there is a combinatorial version there. So what we did is basically use the combinatorial versions of the tools here to prove a result there, and that's why we call this attachment approach. And just one last thing is from this, so after this framework, the main input of our proof is this result by Agavo about this asymptotic behavior of intersection numbers of some called C classes on the modular space, which is sort of surprisingly have some algebraic geometry nature. But anyway, so with all of this been skipped, let me thank you for your attention.